In the second case, we are going to look at a person. This person is going to climb up a very tall building. Okay, is going to climb up a tall building, and they ask you how much energy is used, right? How much energy is used. Now we assume that this person is climbing up the building. There's no friction and so on, right? We just look purely at how much energy is used to climb the building. You read this exercise 5.13.
With what minimum average power must a 35 kg human body generate climbing up the stairs to the top of Washington Monument? The trip up nearly 170-meter tall building takes him 10 minutes. Include only work done against gravity, ignore biological efficiency.
Biological inefficiency, it means what? It means your muscles. Actually, they say the muscles only. Let's say let's say you are moving at you have gained a kind. You run at you are running at 10 meter per second. You are actually running at 10 meter per second. Let's say you have used your kinetic energy is actually maybe 400 joule or something, right? 400 joule. Your energy is 400 joule, but your muscle has to work 4 times that amount in order to produce that 400 joule. So they say the muscle is very inefficient because we have to breathe in, make the lung expand, then let the blood flow to the different parts of the body, and not only to the legs though. You're flowing to the arms, the limbs, every part of your body. So you say it's actually very inefficient. The body is actually inefficient. The efficiency is only 25%. So so you have to actually ignore the biological inefficiency. Okay. So we are purely looking at how much potential energy the boy gained. And we assume that to be the amount the amount of energy spent. Okay, right. So how much energy the boy spent in climbing up 170 meters? So the potential energy is mgy, mass times gravitational acceleration times the height achieved. So the mass is 35, the gravitational acceleration 9.8, and the height is 170 meters. So the total potential energy gained by the boy is 58,310 joule. So this is energy in the form of potential energy. And if this is the amount of energy used, how much is the power? Power is the energy divided by time. Energy 358310 divided by the time, 10 minutes. But you cannot use minute because it's not consistent. So the unit that's consistent is second. So you have to convert the 10 minutes into second. So it's 600 seconds. So energy divided by 600 second, answer is 97.18 watt. So this is the power used to climb up the 170-meter monument. This is the minimum energy. Okay, the boy actually has to eat more to overcome the friction, to overcome his body inefficiency. Any question on this?
No questions.
No. So this one is, we use the second formula, the energy divided by time. Next. Oh, this one is a boat. Oh, this one involves the kinematics. you read this and you go through the working. The working is like that. Okay, let's say we divide it into this. So, okay, so you read through this, then you go through from top to bottom, then here I go down and get a cup of water. My throat is very dry.
Okay, sir.
You read and try out this. I will explain to you. Okay, I'm back. Okay, you read this example 5.14.
What average power would a 1 times 10 to the power 3 negative kg speedboat need to go from rest to 20 meters per second in 5 seconds, assuming a water expert exert a constant drag force of magnitude F equal 5 times 10 to the power 2 Newton, and the acceleration is constant. Find an expression for the instantaneous power in terms of drag force, the mass, acceleration, and time.
Okay, right. Here actually the speedboat is not moving with constant velocity. If it's moving with constant velocity, like earlier on in the elevator, then we can find the force by equating the opposing force. But this is different. This one, the speedboat is actually accelerating, so it has a net force, and it is also overcoming the friction, the drag, the water drag on the speedboat. So actually your force is more than the net force. If you want to calculate the total force of the motor exerted by the motor, it will be the net force plus the frictional force, the force against the drag. So you have to add the two together. Okay, but now they just want to find, in the first part, they just want to find the average power of the boat needed to go from rest to 5 meter, assuming the water exert a constant drag and the acceleration is constant. Okay, right. So we have to find two, two forces. Okay. So in the first case, we try to find out how much is the energy in the form of kinetic energy. Okay, so the kinetic energy is actually half mv squared. Half m is 1000 kilogram, and the velocity is 20 meter per second. 20 meter per second, right? So this one is the kinetic energy. In order to find the work done against the friction, although we know the frictional force here, this is the frictional force, right? But we don't know how much they move in the direction of the force. In order to know the work done against friction, you must use the frictional force times the distance. We don't know how far they travel. So we have to fall back on our equation of motion. Now this equation of motion, since we know the final velocity, the initial velocity, and the time taken, so we can actually calculate the distance moved against the friction from 0 to 20 meter per second. How much is the distance moved? And that distance moved multiplied with the friction will we can calculate the work done against friction or the energy used to overcome the friction. So we start by finding the acceleration. Using the formula v equals to u plus at, initial velocity is 20, final velocity is 20, initial velocity is 0, acceleration we don't know, and the time taken is 5 seconds. So from here we can calculate the acceleration. And the acceleration is 4 meter per second. But actually we don't want the acceleration, we want the distance traveled during that period of time. So using this equation, v square equals to u square plus 2as, final velocity 0, final velocity 20, initial velocity 0, 2 times the acceleration found out earlier, 4, and distance. Distance is the one that we don't know. So we use 400 divided by 8. So the distance traveled is 50 meters. So we are going to use this 50 meters, multiply with the frictional force, then we know how much is the work done against the friction, the drag of the water. So the frictional force is actually 5. Okay, 500. So it's 500. The distance moved 50. So this is the work done against friction, 25,000 joule. Okay. If you want to calculate the power of the speedboat, so the energy is used to overcome the friction and also the kinetic energy gain. So there are two forms of energy. One is the kinetic energy. This is the energy produced by the speedboat. Not only this kinetic energy, but also the energy used to overcome the drag of the water. And this we have calculated it to be 25,000. So this is the drag of the water. This is the kinetic energy. So the total energy divided by the time taken, 5 seconds, right? So the total energy is 45,000 watt. If you want to change it to horsepower, 60.3 horsepower.